Okay, today I'm going to prove all the eigenvalue of real symmetric matrices are real. Okay, what it mean by this question? Okay, I need to clarify the question a little bit. Real symmetric matrix, it means that real here it means that all the entrants on the matrix are real number only, not complex number. Symmetric, it means that transpose of matrix equal to the matrix. So for example, we have matrix B equal to A, B, B, C. We, we transpose them, right? And then we still got the same matrix. So it doesn't change the matrix at all. Okay, we need to use a definition of the eigenvalue and eigenvector for matrix A. So we let lambda 2 be the eigenvalue of A, and V is the eigenvector of A. One important point here is the eigenvector cannot be zero. This is the eigenvector definition. Cannot be zero, okay? So when we have this, so we can just write down a formula. Matrix A eigenvector multiply eigenvector equal to the lambda eigenvector. So this is the definition of eigenvector and eigenvalue for matrix A. Right. So, okay, how can we use this definition and all the information here to show that lambda here is real number, cannot be complex number? Because right now as lambda is the eigenvalue, so lambda can be complex number, can be real number, can be anything, right? So we then assume lambda is real or complex or whatever. So that's why we need to show that lambda is real number, cannot be complex number. Okay, let's use the definition of conjugate transpose. When I say conjugate transpose, it means that we can use a conjugate transpose equal to lambda v, because both sides are equal. We can do the conjugate transpose, right? Because this is the this side is the column vector, right? A matrix A multiply the eigenvector is a column vector. So we do the transpose, conjugate transpose. So we have the row vector here. Okay, this is very important. We can use this later on. So right now we simplify the formula. We simplify the formula first. So we can go to next step. So we have U star A star equal to V star lambda star. Okay, why I switch the order? Because this is a definition of the conjugate transpose. Like if we have a vector, we have two matrices star, so it's equal to A to B star and A star. Okay, I might need to review what it mean by star. Star, it mean that if we have a matrix B stars equal to B conjugation transpose equal to B, or we can do the transpose first and then do the conjugation. Excuse me. They're they're the same actually. So it doesn't matter you do the conjugation or transpose first, they are the same. So B star is this definition. So and also we have if two matrices star, we mean that we need to restore order. Like this is similar like A B transpose equal to B T. So it's restore order A and B. Okay, right now we have this formula, formula here. How can we use this information here? Right. Because this given, we need to use the information here in order to prove something. So because A is real number and symmetric, so it means that A star is just became A transpose, right? Because conjugation here is doesn't affect the matrix because the matrix all the entrants are real number, right? So we can have one example what it mean by B star. If we have B equal to 1 plus 2i 3 4 B stars equal to B, we do the conjugation and do the transpose equal to 1 we do conjugation here plus 2i change to minus 2i because conjugation 3 real numbers no conjugation. So we have this and then do the transpose again. So we have 1 subtract 2i 3 4. So this is the B star. This is the B star definition. Okay, once we clarify the definition, we can use this condition here. Because A is real, so A star equal to A transpose, right? So we can have V A T equal to lambda A is real matrix. So A is real matrix, so A star equal to A transpose. So because A is symmetric, A symmetric, so we can change A transpose equal to A. On the right hand side, we can just copy. A is symmetric. So once we got here, what can we do next? If we look at the left hand side, V star A, and also look at the definition of the eigenvector and eigenvalue of A, so we can just do the, because on here, like initially this is the row vector, right? So each one of them is the row vector. Because row vector, we can row vector and then multiply the column vector. It makes sense, right? So this is the inner product actually, right? So we can just multiply the column vector, which is the eigenvector, on both sides. So this is a column vector, this is the row vector. So is when we do the multiplication, it makes sense. So we can, from this we can factor A, matrix A multiply this vector equal to lambda V, right? So we can have U star equal to lambda U equal to V star lambda star. So we have this. Something need to remember lambda here. Lambda stars is not equal to lambda because we assume lambda can be complex number, can be any number, can be real, can be complex number. So lambda stars not equal to lambda, right? That's what the question you need to prove is lambda must have to be the real number, but we don't know yet. So we cannot use this lambda star equal to lambda. So we go to next step. From this formula, we can see that we can use the inner product definition. We can use this is this lambda this lambda V equal to U lambda star U equal to. So this is a definition of inner product. When I say inner product, it means that if we have U V is equal to U star V. Right now, U V can be complex number, can be real number. We didn't assume anything, so we use a star here. And then we can use a definition of inner product, and we can this equal to this. Why is the conjugate of lambda? Because this is definition of the inner product. if you remember the inner product definition, like if we have u v, c is a scalar, so we have c lambda u v. Inner product have property of first component's linearity, so we can take the c out, but not the second component. Like for example, u c v. We cannot take the c out. The definition for this had to be the c conjugation of u v. So that's why lambda here had to have a conjugation. So we have on the right hand side. So this the star. So we have because lambda star, it means that just a conjugation actually, right? Because lambda conjugation and transpose. Lambda stars is equal to lambda and then conjugate transpose. But lambda is a scalar. Transpose equal to transpose, like 2 transpose 2 equal to 2. Right? So it's equal to lambda conjugation. So we can write it out here. So this is we have this. So we can apply this formula again. On the right hand side. On the left hand side, we can just copy. So this conjugation, we're moving out, we need a conjugate. Conjugate of conjugate equal to lambda, right? So we have this. Okay, for this step, and then what should we do next? Okay, so you might attempt to, because this both sides the same, we can just divide them, right? But one important definition of eigenvector cannot be zero. If this is zero, we cannot just divide them, right? But we know that this vector cannot be zero. It means that lambda, it means u not zero. Right? If this inner product equal to zero, so it means that v had to be zero vector. But we know that v is not zero, so this not zero. So the inner product v is not zero. So we can just divide both sides. We can divide non-zero number. Right? So we have lambda v equal to lambda because u v not zero. Right. So we have this. So the lambda can be real, can be complex, but we have this definition. We have final answer is this. So it means that lambda must be real number. Because only real number have the property, right? because conjugation doesn't change the value. Like for example, if lambda equal to 1 plus 2i, lambda conjugation equal to 1 subtract 2i. So lambda not equal to lambda conjugation because we have this. But if we don't have the imaginary component, then the conjugation doesn't change the number. So we prove that lambda must be real number. So this is the final step. That is the final step actually. So we finished the proof. Okay, thank you for watching.